All right, just like I told you in the last video, we're going to start this video with some ways that we might be able to use that relationship between a function and its inverse, or at least the derivative of a function and its inverse. So for example, if I gave you a function such as this, f of x equals x cubed plus 2x plus 7. If we try to find the inverse of that, if we switch the x's and the y's, it's really difficult in this case to isolate y. In fact, I don't know how to do it. So in this case, finding an inverse is going to be difficult. But if I asked you, so if the question said, find the derivative of the inverse at 10. Well, that one's going to be interesting to find because I don't know how to find that inverse. But we do know the relationship between the derivative of a function and the derivative of the inverse. So what that means is, in this problem right here, we know that 10 is the x-coordinate of the inverse. We don't know what y is, but that's okay, because what that means is, in the original function, the y value is 10. So if we can find the x-coordinate that will make the y value 10, then that's going to make this problem very easy, because we have that relationship where the x's and the y's are switched. So if x was the input for the inverse, if 10 was the input for the inverse, 10 is going to be the output for the original. Well, I'm just going to tell you now, and I'll show you other ways to find it in a minute, but I know that when x is 1 in the original function, the output will be 10. So that means then in the inverse, if 10 is the input, 1 will be the output. Okay, so let's see if we can find the answer to this question. I know that the derivative of the original function at 1 is the same thing as 1 over the derivative of the inverse at 10. That was the relationship we just saw in the last video. As long as we're using that point that they share or that they have in common, then that's true about the relationship between these two functions and their derivatives. So let's find the derivative of the original function, because all we need is the power rule. F prime of x is 3x squared plus 2. F prime of 1 is 3 times 1 squared plus 2. So the derivative of the original function with the input of 1 is 5. Because of the reciprocal relationship we found in the last video, I know then that the derivative of the inverse at its input of 10 will be 1/5. Okay, what about, let's do a problem like this. Let me number these now because I don't want to use a different color. I like this green. So what if I get a function like this? I'm going to use something different than f because I'm tired of f. G of x equals x cubed minus 10. Sorry, I'm kind of making this up as I go. So if I'm going to try to find the derivative of the inverse of this function at -2, I could go about finding the inverse of g of x. I really could. That would be something that is absolutely doable. In this case, we can find the inverse. But let's look at the relationship, the reciprocal relationship instead. I know that in the inverse, the x-coordinate is -2. I know that in the original function, the y-coordinate is -2. So if I can find the input for the original function, I can just find the derivative of that. So let me show you what I mean. We know the y-coordinate is -2. -2 equals x cubed minus 10. If I add 10 over to the other side, I get 8 equals x cubed. And I now know that x is equal to 2 in the original function. So I can fill in the x and the y coordinates with what I just found. I know that x is 2 in the original function. That means that y is 2 in the inverse. So if I'm trying to find the derivative of the inverse at -2, I can find the derivative of g, which is a nice, easy power rule. And if I replace x with 2, 2 squared is 4, 4 times 3 is 12. I know the answer to the question then. I know that the derivative of this function at -2 is going to be 1/12. They have that reciprocal relationship. And if you can't find an inverse, or if it's not convenient to find an inverse, we can always just do this method that we just did here. We knew the x-coordinate of the inverse, so that means that's the y-coordinate of the function. Finding the x-coordinate of the function allows us to find the derivative then. Okay, let's try one with no functions at all. I kind of like this red, I'm going to stick with it. We know this. We know that f of 5 is equal to 9, and f prime of 5 is equal to -3. So this stuff is given to you. You know this is true. I want you to find the derivative of the inverse at 9. I want you to pause for a moment. I haven't had you pause yet. It's time that you pause. I want you to think this one through. I don't even tell you what the function is. You can't find the inverse algebraically speaking. So how can you find the derivative of the inverse? Pause for a moment. Go try. Welcome back. I hope you tried it. So here's some information we know. On f of x, we know that f of 5 equals 9. So we know we have an ordered pair, 5, 9. And we know the derivative at that x value. We know the derivative at 5 is -3. So if we look at the inverse then, there's also some stuff we know about that. Since the point on the original function is 5, 9, I know that I have a point on the inverse that is 9, 5. They have that really great relationship where the x's and y's are switched, which means then I can, in a pretty straightforward way, nothing I have to calculate, I can find the derivative of the inverse at 9 to be the reciprocal, -1/3. Didn't even need to know the function, I just needed to know that there was that really interesting relationship between the derivative of a function and its inverse. Okay, I think that's enough. Go give it a try.